cell in the memory, and then we can read or write using the bit or bit bar lines that we have in the circuit. And when you are reading, then it goes to the sense amplifier, and sense amplifier senses the difference between the bit and bit bar line potential, and then that tell you the whether the stored value is 0 or stored value is 1. Then we looked at the functional model for this particular circuit, and the functional model is that you are supplying an address, and then that address goes to the address decoder, that is in terms of row decoder and column decoder, and that accesses the memory array, and then the excess memory array will be delivered you to the output. That's the simplest or functional model that we can use. And so looking at that, we have developed four kind of fault models, or simplistic fault models. There can be very complex fault models that you can develop out of it, but those simplistic fault models are stuck at fault model, wherein we assume that any storage element can stuck to logic 0 or logic 1. So that means if I can always write that particular cell with 0 value, but I cannot write 1 there. Or if it is stuck at 1, in that case I can write the logical value 1 over there, but then I cannot write logical value 0. The other one is the transition fault model, which says that the cell may not be able to transit from one value to another value within that period of time in which it is supposed to operate. So so this can be if the transition from 0 to 1 or 1 to 0. There can be a coupling fault model that can say that because here we are running the long these coupled lines, so there can be a coupling between the two cells, cell I and cell J, and then any activity on or any change in cell I can change the value of cell J. That's the called as the coupling fault model. And then now coupling, simplistically we are assuming that one cell can be coupled with another one cell, but this can be generalized. One cell can be coupled with any number of cells, maybe two cells, four cell, eight cell, or so on and so forth. But and then the more complex fault model here is the neighborhood pattern sensitive fault, wherein you are looking at the neighborhood of a cell, and then look at whether the fault is there or not. So for that we looked at the two state diagrams yesterday. One is state diagram of a single cell, that how it transits from one state to another state on the request of write, and another one is the faulty. So faulty cell that will give you the transition diagram like this. There can be only one state, second state it cannot transit to, and therefore now you have to check whether these how to distinguish these two. And in order to distinguish these two, if cell is in state S0, and then if I write W1, in that case it is supposed to go S1, but here it will again go to S0, and therefore now the test that I can conduct for this would be put the cell in state S0, and then so that is the initialization condition for this particular memory cell. And then you provide the the input W1, so that means you write 1, and then check observe the output, that the if output is 0 or output is 1. If it is 0, in that case it is say so first sorry, maybe I should write here, write 0 on this cell. Then I have to say ascertain that whether this whatever we have 0 we have written, that 0 is it is still keeping or not. and then I will write one, and then check whether this one would be there or not. Now this sequence can help you in identifying whether the cell is at stuck at 0 or not. On the contrary, for stack at one that we have developed yesterday, that the both of the faulty and fault free circuits will have one state common, that is S1. But then on S1, if I give input as 1, in that case it will continue to stay in the same state. However, if I give input 0, in that case this is supposed to transit to the another state, and we can check observe the output. So that means I have to first write 1 into this cell. Then after writing this, I have to ascertain whether this has 1 or not. So I have to read it and compare against 1. And once it is confirmed, in that case I will write 0 and then check whether it is returning the 0 or not. And this output will tell you whether the cell has a stuck at one fault or not. So if I can have this, in that case I can find out whether there is a stuck at one fault or not. So these are the two essentially say methods, or two ways in which we can test the stuck at zero fault or not. In the similar way, here you can develop the test for the transition faults. For the transition fault here, maybe you can see that in the good machine, the say good or bad machine, both machines will contain both of the state as 0 or as 1. However, the good machine can transit from state as 0 to as 1. However, bad machine cannot transit from as 0 to as 1. Whereas bad machine can transit from S1 to S0, right? That's where these two differ. So now here, if I want to make or develop the test for this, what I have to do is, first I have to ascertain whether this cell is in state as 0 or not. So that I can ascertain by writing 0 to cell as cell I. Then I will read and check whether this has this is returning 0 or not. If it is not returning 0, in that case I can go for then. So if I ascertain this, then I can go for this particular transition, right? That transition can distinguish between the good and bad cells. And therefore what I need to do is I will write one, and then check whether this is having returning the one or not. And if I apply this test, in that case this test can say test this particular fault. So this is the transition fault, wherein I can check whether this cell is transiting from say 0 to 1 or not. So this particular transition fault, we are writing that here, when I make a transition from 0 to 1, the cell is to. So that is the transition. So now if you look at yesterday, we have gone through the sequence of operations, because we are not only interested only in checking individual one cell, whether that is good or not. We have to check whether entire array is good or not. And to check, maybe you can do this with like a multiple operation with one particular cell. Now what you can do is, you we can, when we start to when we open one particular line, in that case I will keep on writing to all the elements. So first you can say, if there are multiple cells, then you can write everywhere 0 0 0, like this. And then you come and read whether this value is 0 or not. If this value is 0, in that case it is fine. If it is not even if it is not 0, in that case something is wrong with that. And after that you have to read this and then replace with 1. And so now here from cell, you in any one of the order, either the increasing order of the address or decreasing order of the address, you can go from 0 to n minus 1 or n minus 1 to 0, and write everywhere first 0. Then second time you have to read this to ascertain that it is returning the 0, and then write 1 and see whether this will strike to 0 or not. So now, now you write 1, and after writing 1 you have to read 1. And so in this way, if I go through this, it can check all, like so here you can see that this sequence is implemented in this. And hence now you can say that here w0 r0 w1 r1, this can say test whether so in the first one is stuck at 0, and another is stuck at 1. Now stuck at 0 will be initiated when I apply this w1. So in M1, when I apply W1, in that case, it will excite that particular condition, that the cell which was at logic 0, now I want to write 1, whether it is going to state 1 or not. And then it is detected when I use this M2 in the second march, when I apply R1. So this is the excitation condition, and this is the detection condition. So the fault is excited by this march M1 when I use write 1 in that, and then detected in this R1. Now for stuck at 1, it is now where I'm writing 0 over here. So the fault is excited in the March M0 when I'm writing 0, because this cell is not supposed to have 0 if there is a stuck at 1 fault. Now, I'm writing this 0, and then it is detected. When I'm detecting, in that case, I have to observe the output, and then output I'm observing in March M1, and that is R0. So this will give me the fault activation. This condition we called as fault activation, and this is fault observation or detection. So if these two conditions, and both of these conditions are covered in this case, in that case this the simplest mass test mats can cover all these. And with every cell I need to do 4 operations. One is w0, another is r0, w1, r1, and therefore the total number of operations that I need to do is 4n, if n is the number of elements that I have in my circuit. And hence this test is also called as 4n test. 4n test means I have to apply 4n operations to test this. Can detect the stuck at faults which can be possible in memory arrays. Then maybe I'll come back to this test. But again, again, this is, then it was augmented to match plus, wherein one more operation was added as W0. In terms of the stack at fault detection, this carries no extra, or this cannot detect any extra thing. In this case, one more thing that can happen is I can detect the transition fault, that is this transition fault. stuck, I mean, transition from 0 to 1 can be detected, because the same sequence I'm applying W0, R0, W1, R1, that is needed for this sequence is needed for say to test the transition fault, the wherein it is not transiting from state 0 to state 1. So this can this particular test can say cover all stuck at faults and some transition faults. So this is the coverage of this. Now when I have a memory circuit I mean has some more element, not only only the. So this test we have covered mats, that is like a 4, and I have to apply four operation with every state. Now this arrow, up and down arrow, these will come into picture when we look at the other things. So in see this memory, I have this array here, but along with array there are decoders. Now when you have decoders, right, what can happen? There can be a fault in that. Decoders are the combinational logic. Now when you can say that here, oh, this decoder is a combinational logic, I can separately test decoder using any stacked fault model for the decoder faults. Yes, of course you can do that. However, uh, we know that decoder has a very specific functionality. What it does is it has to get input stream of bits, zeros and ones as input, and then generate the address of that particular row and column wherein wherein your cell is placed, and it has to excite that particular cell. Now, if there is something wrong with the decoder, what can happen? If everything is okay, in that case, if my say address is ij, in that case, it will excite a row, ith row and jth column, and the cell which is sitting over here would be excited, and I can read or write that particular cell. I will read only that particular cell. But if something goes wrong, in that case, what can happen? That either either this decoder that is uh, decoder that I have, that is I give the address ij, and will excite it's supposed to excite ith row and jth column. If it does something wrong, and then this can change, this may excite ith row and kth column. In that case, what will happen? This will ith row and kth column. Now I am reading or writing some another cell, right? And if you are reading or writing another cell, in that case, maybe you are expecting, because and that's why, so when we are doing this, we are reading and writing into this cell. Now if you write to the another cell, in that case, what will happen? That it will write this into it. It will, after, say for example, after this one, after W0, it will write 0 everywhere. After that, it will read this. If here it has written 0 everywhere, assume first assume that there is no fault in the array wherein you are storing the value. Only fault is with the address decoder. When fault is with the address decoder, you will go and then say, after the second test, you are reading that. So in place of you are reading this ij, you will read ik cell. When you will read ik cell, you will read the same value 0 is stored over there. You are happy with that, it passes your test, and then you are writing there, so it will write 1 over there. Now, when you will go to the kth cell, my decoder will give me the correct address, and hence now here I was supposed to read value 0 from there, and now it is storing value 1. So now here say this is ith cell, has I mean this kth cell, kth row, ik. So now I was supposed to read 0, but now I am reading 1, because earlier I in place of writing ij, I have written 1 to ik. When I will go to ik, I will read 1. If I read 1, in that case I will say that here there is something wrong, because it doesn't match. I was expecting 0. Maybe you may get just the false signal that what went wrong, but at least you know that something has gone wrong. It is not correct, and therefore now here you can capture the decoder fault as a side effect of testing of the array, and therefore you don't need to apply additional test to test the address decoder. That's the main theme over here. So what can happen, like here, in place of ij it can point to ik. In place of ij, perhaps it may not point to anyone. It may not read, I mean point to anyone means here it may not write anywhere. It, if it don't write anywhere, in that case it won't read anything, and therefore there can be a something can go I mean can be detected. Or one cell like here can be coupled, give two addresses, ij or ik. That is also possible. Or this one can be ij or pk, pj, something like that. The multiple can access the multiple. So all these can be captured or can be tested as a side effect of testing the array. To that, detect all the address decoder faults. This means that apply the number of reads or write operations. Before condition 1 must have write something into the element. X can be 0 or 1, so this can be write 0 or write 1. And so what you do, so here you read the array and then write the opposite value of that. So if I go through this, say from the 0th to n minus 1 element, first I read and then write. So read and so read, if I say Rx, then I will write Wx bar there. If I do this, and one more time, if I start from the last cell, I will go to 0, and first I read X and followed by write X bar. So these two, if I follow, I do this in both ways, from say 0 to n minus 1 or n minus 1 to 0. In that case, it can capture all the faults which are possible in the address decoder, because the first condition, what it says, that if there is a cell, if in this case, if you say in place of ij it maps to ik, ij maps to ik, and if k is greater than j, then this will capture that. Condition 1 will capture that. Because I have, so say for example, ij is 1 1 and ik is 1 3. So that means like whenever I was accessing 1 1, I have written the to I3 1 3. And when I will go to 1 3, in that case I will find the different value written over there, and hence I can capture that particular fault. However, so this can be captured by condition 1. If k is less than j, in that case that is captured by condition 2, exactly in the similar way. Therefore, for address decoder fault, you don't need to do extra effort. The same effort can help you in testing the address decoder, and now the this the your say any fault that we are detecting, like here this R0W1 and R1W0, and therefore now in this one we are in one of the ways we are going. So let's look at this test. I'm going in forward way, 0 to n minus 1, reading this value 0 and writing value 1. But in the reverse way, when I'm coming, I'm only reading, I'm not writing. And therefore it can detect only the address decoder faults which are possible when there is a coupling from ij to ik, wherein k is greater than j. So not sorry, coupling, the decoder fault. But so this can satisfy only the condition 1, won't satisfy condition 2. Therefore, if I can augment this with this one additional say right R0W1, this satisfy your condition 1 of the address decoder. This will satisfy condition 2 of the address decoder fault. If it satisfy both of these, in that case it will also say detect all the address decoder faults as well. So therefore, if I augment this MATS algorithm to MATS plus, wherein this becomes like there are 5 operations you have to do with each and every cell. Those 5 so and therefore I call this test as a 5N test. There are 5 operations you are doing with every cell, and that 5N algorithm can make it possible to detect the address decoder faults. So now if you look at this, the MATS plus will give you, so this is 5N test that can also detect this one. So like this, uh, so here this table summarizes that MATS can detect all the say address decoder fault. This and some of the no sorry, all stack faults, some of the address decoder faults, also detect some of the transition delay faults. Sorry, not transition delay, transition faults in the circuit. If you go for MATS plus, this can detect all address decoder faults. And MATS plus plus maybe now you can go and analyze. In MATS plus plus, what do we do? Uh, in MATS plus plus, we are adding one additional, that you are reading the one, writing 0, that is up to that it is same as MATS plus, but in M3 you are also reading that value 0. This can give you the possibility of the test of the other transition fault, that is transiting from 1 to 0. This can also detect the whether it can transit from 1 to 0 or not. So that that's where it performs. So now here various algorithms, you can see that the algorithms, the simplest algorithm is for n, where n is the number of cells that I have, and then you have all the kind of say algorithms. We have algorithms which are up to 43n. That means 43 operations we are applying with every cell. You can compute that here how many operations you may need to I mean how much time it will take to apply those many operations, because you know the frequency of operation of the memory, and you know that how large memory is. So you can say apply those. In general, memory is the byte readable or writable. So we are at a time when we are writing or we are reading or writing a byte. We are not reading or writing an individual bits. So you have to apply I mean on a byte, and therefore you can compute how many bytes we have in the memory. So n is the number of bytes that we have in the memory. uh, Sometimes, like it used to ask, I don't know, some of the laptops still they might be asking that whenever you power your laptop on, it asks, generally it tests the memory, that how which algorithm you want to use, whether you want 4n, 5n, 52, I mean 43n, 10n, 15n, and you can choose, and it will quickly run that algorithm and tell you whether your memory is good or not. Now maybe one can say that here, if I know that, how I mean what I can do with this. If you know that I mean memory is faulty or fault free, now I cannot throw out that memory, right? What to do, because that is already integrated in the system. So in that case, you can, if then you have to diagnose that where what kind of fault is there, and in which cell there is a fault, and if I can identify that, in that case that particular row or column we can exclude from the memory. So that means here we won't write into that, and we can remap the memory. So that is called as the memory with the self repair capability, uh, being widely used. And for that, now I mean here I'm telling you that how you can test, you can apply this test using the tester, right? But when you are powering on your computer, at the time you don't have tester with you. So therefore there should be some mechanism through which you can apply without using the tester, and those are called as built-in self-test. I think Professor C.P. Ravi Kumar will cover that part in a day or two. So perhaps this was the say depiction of the same thing, that let's say that here, if there is a fault in cell 2 1. So cell 2 1 is in the second row and first column, and fault is stuck at 0. Initially we are writing 0 everywhere, the say March M0. So you start to write from say 0 to 9th cell sequentially. And then what you do, you look at, read that value. So in M1, what you are doing, you are reading whether that particular cell will have 0 or not. If it has 0, in that case, after that it will write 1 over here, and then you can write everywhere. Now you go to the third March M2, and then what you do is you read whether this contain 1 or not, and then after that you are writing W0, that is March Mats plus, which is 5 an algorithm. And keep in mind that if I augment mats to mats plus, it can also detect all the address decoder faults. So now I'm reading whether it has one or not. I mean, and so so the good machine is supposed to give me this one. If machine is bad, in that case this first element, the 2 1 cell is stuck to logic 1, and hence when you are writing in the first march m0, you may not be able to write onto this particular cell 2 1, because this cannot hold 0, this can only hold 1. So that means like it powers up in state 1, and then it will continue to remain in state 1. Interestingly, most of the say memory cells are powering up into some particular state. Some are powering up into state 0, some are powering up into state 1. And generally that gives a signature of the memory, that what kind of memory you have in case you need that signature somewhere. Now when you are say so this is the bad machine. When I look at this, I read in my say M1, because this is my excitation condition for stack at 1. M0, it excites the fault, and M1 it should be able to detect. Now when I'm reading this again, I'm supposed to read this R0, and after that I'm writing 1. When I'm reading R0 here, you will read that this value is 1, and hence there is a stuck at 1 fault over here. So this is how you can test it. So these are the address cell example you can go through. I have already explained you. So this is how, maybe there are more complex faults. Now you can go through this on your own. This can, I mean, this has, I believe, has given you a reasonable idea that how you can develop a test. In order to develop a test, you have to first look at the excitation condition, that how fault can be excited. Now we know the faults are the stuck fault, transition fault, coupling fault, and the uh, the pattern sensitive uh, neighborhood fault. So these are the faults. So what I need for excitation, that the difference between the two machines, in which state it differs. First, you have to initialize into that state and then apply a transition. Now that transition will act as a excitation. Once I apply the excitation, in that case, at the end result of that is that good machine should transit to one state, bad machine should transit into the another state, or so. Therefore, now you have to observe. So that means after that you have to observe. I mean, excitation means you have to write something onto that. Observe means you have to read, and after reading you can figure out that here whether that particular fault is there or not. This is the way we craft, or we decide that how I can test a memory cell. So memory is in general tested functionally. So mostly these are the functional uh, tests for memory. So it can cover, like here, maybe one can say that, for why I need to go through so many say operations with one particular cell. So like here 43N, or maybe you can go even beyond that. That is one question one can have. Another one is, how why I give the restriction that in one time I have to go in the rising address, and another time I have to go in the falling address. So that means here it is 0 to n minus 1, and here n minus 1 to 0. Why this is necessary? Of course this is not necessary. You can go zigzag like this. That is fine. But you have to revert back through the same path in the another march in order to ascertain that you are able to detect all the address decoder faults as well as the coupling faults, because coupling faults, there is a coupling of one cell with the another cell, and to find out the coupling between one cell, like here you have to excite in one, so that means here when you write in one cell, the value in another cell will be upset. Now that value of the another cell which upset may have address more than this, or that may have address less than this. If it has address more than that, so in that case exactly in the like a decoder kind of fault, you say in the rising order of address, you can detect if the coupled cell is has address higher than this, or that coupled cell we also call as the victim cell. So victim cell has address higher than the current cell, or I can catch that when coupled cell or victim cell has address less than this, when I go in the following sequence of address. But really it doesn't matter what sequence of address you are using. Only thing is you have to ascertain that the path through which you are going, you have to come back through the same path. That's the bottom line. Regarding large number of operations, so for example, there are some fault models that I have not discussed over here. One is the what it says is that if you are reading your that happens typically in DRAM. If you read the memory cell multiple times, in that case it may lose its charge and then it can flip its value. Multiple times means here if you are successively 5 times you read that particular memory, in that case it will lose the charge and it can flip value from 1 to 0. So that kind of condition. So now in order to excite that, what I need, I have to at least read that 5 times continuously, right? And after that uh, I 6 time I'm reading, in that case perhaps I would be able to get that. So that means here at least you have to do 6 operation to detect that particular fault. So these are, I mean, so those are the kind of faults like the read destructive faults and etc. They need to have perform more operation with a single memory cell, and therefore the number of operations will increase. If number of operations will increase, in that case the time taken by that will increase. Like the difference between 4 and 43 n is 10 times. So if one is taking 10 seconds, in that case another will take 100 seconds, right? So that will really large, humongous, or the it has direct implication in terms of cost. Okay, so I close this discussion at this point in time. If you have any questions, I would be happy to answer. I don't see any question. Oh,
Sir, there is a question in the chat box, sir. Mr. Pankaj is asking the question: what is the difference between functional and behavioral testing, or are both of them same? That's the
functional
question.
functional and behavior test, we assume when we are referring to the same thing, because the functionality is same as the behavior, right? The functionality for which you design a circuit, it gives you that behavior. So the functionality of a memory device is to hold the value, right? The behavior of the if I look at the behavior of the memory device is what, that it is supposed to hold the value. If I write 0, it should retain 0. If I write 1, it should retain 1. And if I go from 0 to 1, in that case it will record that value, that transition, right? So functional and behavioral are one and the same thing. This is just the terminology. Some people like one terminology, some people like the another terminology.
Thank you so much, sir. So dear participants, if you have any more questions, please feel free to ask.
Yeah, most welcome. If you don't ask, in that case, really it may not be that fruitful. All this material you will find in any textbook that you use.
So, sir, there is no question. If you want, we can have a 5 minutes break, sir.
Okay, we can have 5 minutes break and then can you start at 10 o'clock?
Yes, sir. Thank you so much, sir.
Okay.
So, dear participants, let us join sharp at 10 a.m. Thank you. So, good morning, sir. Can we start it now?
Yes, yes.
Okay, sir. Thank you so much.
Hello.
Yes, sir.
So shall we start?
Yes, sir. Yes, sir. Thank you, sir.
Was there any question? You were saying something.
No, sir. I was just requesting if we can start it again. That's
Okay.
there is no question. Only one question was there. You have already answered that.
Okay. So if there's no question,
So I
then
request participants to please actively post, keep on posting your questions so that you can get benefited out of the expert talk. If there is some doubt, definitely sir is going to clear it, and it will be the help for all of us, not only for the person who is going to put the question, but it is the lesson for all of us. Thank you. Yes, sir, please.
yeah. So now the next topic is sequential circuit test. Uh, so first thing is how we define a sequential circuit. What is called as the sequential circuit? So sequential circuit. Let's say that here I this is making too much noise. So if I have a a circuit, if I define the behavior of the circuit, wherein I define the behavior of the circuit which is dependent on the instantaneous input that it is getting at that given point in time. Output is determined by that. We call that as a combinational circuit. So output is decided by the combination of the input that we are applying. Now therefore, in order to define the output, you have to define for all possible combination of the input, and therefore we can use a truth table to define that. That for if you have n number of inputs, in that case truth table will have 2 raised to the power n rows, wherein you are defining that how it will how it will behave. However, there are some there are some cases wherein you cannot define the behavior combinatorially. That means that that particular system has circuit or system has a behavior that has some kind of temporal requirement. For example, if I want to define the behavior of a say uh, traffic light controller, in that case traffic light controller has to produce a sequence of signals, and that sequence goes from say green to yellow to red to green to yellow to red, and so on and so forth, right? So there is a temporal behavior, so temporal behavior has to be encoded. Another example can be like, for example, if you have a vending machine, and that vending machine has only one slot through which you can insert a coin, then because different commodities may cost, say if it delivers you only one commodity, and that commodity has fixed price, and that for that fixed price you can have only one coin, and say that restrict that it will accept only that particular coin, won't accept any other coin. So for example, if it you say that here the commodity has price 5 rupees, and then it can accept only 5 rupees coin, in that case the behavior is you can define that, say combinationally, that whenever you get the 5 rupees coin, detect the 5 rupees coin and dispense the commodity. However, if it has to dispense multiple commodities may have different cost, and therefore it has you have to insert multiple coins. If you need to insert multiple coin, in that case you have to define the temporal behavior, that it has to memorize that what you have already inserted in that, and then whenever it collect the enough money, in that case it will dispense that. So uh, so this one now the so this sequential circuit will have a temporal behavior. Now, so how I define the output of a circuit y, that is a function of the current input that I am getting now, as well as it is function of the past inputs that it you have received, because that's how you want to remember that here, wow, what is sequence of inputs you have seen. So past inputs. Sometimes people confuse, they say that here the sequential circuit's behavior is that the output dependent on current input and past output. It is not dependent on past outputs, it is dependent on past inputs. That is you are receiving. So now how many past inputs you can it dependent upon here, that define the length of the machine that you have. Now every machine in this case will have some say kind of memory, because it has to memorize that what past inputs I have received, and that therefore to memorize these past inputs, you have to define a state of the system, that say for example in vending machine, whether you have received 5 rupees, or you received 10 rupees, or you received 20 rupees. So what are the distinct values that you can receive, and based on that you can define the system different system states. And then you have to so you have a state of the system, and then now here with the new input, the state of the system has to be modified, and then output it has to I mean the output has to be defined with every state and the input. And therefore any state machine is represented using a tuple that says that this is as 0. As is the set of states, how many states you have in your system. Then the S0 is the initial state from where it is starting when you power on your device, and then a set of input that you are getting. So these are the input symbols. Like here, for example, if you are making a vending machine, and vending machine if it can receive the 5 rupees or 10 rupees, in that case it can receive three symbols. Either it receives 5 rupees, or it receives 10 rupees, or it doesn't receive anything, right? So there can be three symbols. Those are the input alphabets it recognizes. And then output, this may produce some output depending on what input you are giving. So for example, in vending machine case, it will give you the output as whether it will dispense the coffee, or dispense the commodity, or doesn't dispense the commodity. In case of traffic light controller, it can change the light from green to yellow to red. So output is the color of the light. And so those are the outputs. And then it has to have a function that can modify the modify the state, because when you receive the new input, say for example, I inserted 5 rupees coin in the vending machine, and then again I insert 5 rupee coin. In that case, my state will become the 10 rupee state, right, wherein it can hold. And then I insert 10 rupees. In that case, it will transit to the another state wherein it memorized that it has received 15 rupees. So that is the function, transition function, that can change the state. And then the output function, which produces output, and our output is the O, right? So now they this define a state machine. This is state machine. Now here it has two functions. This function delta, that maps from a set of state and input to a set of state. The output can be mapped from the set of state and input to the output, or this can map from state to the output. Based on how the output function is being mapped, we call these machines as milli machine or Moore machine. The first one, wherein the mapping is from state and input to the output, is called as milli machine. And wherein the output is only dependent on the current input. In that case, we call as Moore machine. Any milli machine can be converted into Moore machine, and Moore machine can be converted into milli machine. This is the background of a sequential circuit. Now in sequential circuit, what I have a state. So in order to memorize the state, I need to have a set of storage that we uh, storage that stores the value. And for storage, we are using the flip flops. And perhaps I don't know whether it was discussed, but we are only allowed to use D type flip flops. No other flip flop is allowed in a practical scenario, maybe in industry. And I will tell you that here why that restriction is. Why we can use only D flip flop, not any other flip flop. So you have storage element. Storage elements have a clock. Then there are two logic. One is your next state logic, and another is the output logic. Now storage will go to this state, will go to both. And then output here will come from, this is the input. This will produce output, and then input can go to only to this delta function. In that case, that machine is a Moore machine. If it goes to both, in that case, that machine would be a milli machine. So we can represent a machine like this logically. Some storage, some function that can transit or change the state, and some function that can modify the outputs. Now the question is, I design such kind of machine, and at the end I want to see whether the implemented machine is same as the desired machine that I have. Now how I would test? For combinational circuit, you must have discussed. This is a combinational logic. I have some inputs. There are some inputs, and then there's a output. Let's say this is y, and these are x1 to xn. Y is function of x1 to xn. You want to find out if there can be a fault over here. That fault is stuck at 0, stuck at 1. Now if a fault is there, in that case, I have to test this particular fault. If this exists, in that case, it should give me the some different result. So I want to find out a set of inputs which can give me the distinguishable fault free and faulty output. so that I can distinguish whether the machine is faulty, a circuit is faulty circuit or non-faulty circuit. In order to do that, maybe you have gone through the combinational ATPC using the D algorithm or PODEM or something that you have already discussed, or Boolean difference method. X1 to Xn and output is Y. So now, and there is a fault over here. So first thing is, in order to test this particular fault, what I want that I want to find out a value of input x1 to xn such that the output that for that particular input should be distinguishable whether when I have say faulty circuit or when I have fault free circuit. So, and we are assuming that there can be one fault at a time, there cannot be multiple faults. That's the assumption. That's why we use the single stuck at fault model. Single stuck at. So that means here only one net can stuck to either logic 0 or logic 1. Now, so aim is to find out the value of x1 to xn such that the value of the output would be different when circuit is faulty and when circuit is fault free, and so that we can say that or we can classify the circuit as a faulty circuit or fault free circuit. In order to do this, it has to go through 3 steps. First is fault sensitization. That means I have to first sensitize that fault. Say, for example, if this point is stuck at 0 fault, and if I apply at that point value 0, will it propagate or will it produce the output like here? For example, here I have this circuit and this is stuck at 0, A and B and C. If I apply 0 at A, in that case, is there any possibility to produce the two different outputs for any input of B when when there is a fault or when there is no fault? If this value is 0, in that case, output will always remain 0, irrespective of whatever value of B I have. And whether it's a faulty or fault free, so I cannot distinguish that. So I want to find out a distinguishable input that can provide the different output. So that means here this should be at least at the fault site, this point wherein there is a fault we call as fault site. This is the fault site. So now at fault site I have to have opposite value of the faulty value. Faulty value we are assuming we are generating the test for all possible faults. So at a time we are assuming only one fault. So one time we are assuming that net is stuck to logic 0, another time we assume that that net is stuck to logic 1, and therefore we have to develop the test for different faults. So now I have to have the value, different value at the fault site. So opposite value, so that means here the stuck, if fault is stuck at 0, in that case it should be 1. Opposite value at fault site. If I use opposite value, in that case there is a possibility, I'm still saying that there is a possibility that I can get the distinguishable output at the primary output. Now this, if this fault happens to be at the output, in that case you can directly observe and there is no problem. That's what we were doing in memory test. Memory, every cell you can read directly anytime. In that case there is no problem. It has good observability. You can observe anything at any point in time. However, in combinational logic that is not the case. the circuit is deep, and it has to go through a chain of gates. And if you are not at the primary output, in that case the prop I mean the you cannot observe at the intermediate points, and therefore you have to move this fault effect from a fault site to one of the primary outputs, and that we call as fault propagation, because you have to move that to the one of the primary outputs. And this fault propagation is so I mean, there are various outputs. Circuit has multiple outputs. You can propagate to any point, and it has to go through a sequence of gates. In order to propagate, what you need to do is you have to have non-controlling value on the off inputs of the other gates. Like here, for example, if this is my circuit, in that case, on this is called as the off input, the other input of this gate. This should have non-controlling value. Non-controlling value means here the value which cannot determine the output. Like for example, AND gate, if value is 0, in that case that determine the output, so that we call as controlling value of that particular gate. If I apply 1, in that case that 1 doesn't determine the output, then output will dependent on the other input, right? So therefore you have to have a non-controlling value at these off inputs to this path. So this is a propagation path that we have. Now this is first gate, so you have to have non-controlling value here, that is 1 in case of the AND gate, and then the non-controlling value here, that is the OR gate, 0 here, right? For OR gate it is 0, for AND gate it is 1, and therefore it will define the test vector. So test vector here in this case is 1 1 0. So now say in this case I apply these two, and then fault sensitization and for fault propagation is sufficient. You can say apply any I mean you can apply this test, but assume that this input was say also coming from here. There are two more inputs, C and D, and this is E. So now C and D, because I need zero value over here, and I cannot apply zero value over here, and therefore I have to go all the way to the primary input. If I need to go to the primary input, that means your primary inputs are at the same level in a given circuit, and therefore this so you have to go back from here to primary input, and I have to apply at least one of the value as 0, another value can be anything, and therefore my test vector can be 1 1 0 x, or 1 1 x 0, right? Either one is fine. So that is called as the line justification, because you have to go all the way to the primary input to so all the way from the fault site wherein you, or the gate wherein you need to justify value, to the primary input and apply that value at the input. So this I'm just like summarizing whatever has been discussed in the last class. So these are the three steps you have to take. All the algorithms which are developed are based on this principle, that you have to sensitize the fault, you have to propagate the fault, and you have to justify the unjustified values at the intermediate points in the circuit. This has two essential component. One is line justification, and another one is the fault propagation. Line justification and fault propagation both are the decision making processes. Decision making processes means, like for the fault propagation, there may be multiple outputs, and you can propagate fault to any of the output. Now through some path it is easy to propagate, some path it is difficult to propagate, and through some path you may not be able to propagate, right? So if you are not able to, so then you have to make a decision through which path I have to propagate. And now if you are not able to propagate, in that case you have to come back and explore the other possibilities, and that result into like here, when you find that I'm blocked, I cannot go ahead, therefore you have to come back and then you start to explore the alternate ways. Those are the I mean those result into backtracking, and backtracking maybe then you can go in say infinitely long to generate the test. So this is the like the fault propagation and line justification. Both of the problems are decision making, and decision may be correct, decision may be wrong, and because I mean due to the decision making, the process becomes very complex. And this problem was proved that this is a NP complete problem in terms of complexity theory. This is a non-deterministically I mean deterministically you cannot do solve this problem in polynomial time. Non-deterministically, of course, you choose one in vector, and that vector may be the test vector. So in even in one shot you can get that. So this was proved way back in late 70s or early 80s by Professor Fujiwara. I happen to be his student, so feel good when we talk about the complexity of the circuits. So then this but what makes it say difficult, that is fault propagation and line justification, because both are the decision making process. And this was maybe this is not the part of the discussion over here, and we are not using the set best, but this problem was mapped to the three set problem, and three set problem is NP complete problem. Hence this problem can be considered as the NP complete problem. Now, when it is NP complete problem, that means you cannot find an algorithm that can run in polynomial time and solve this problem, and hence we have to use some kind of heuristics. So almost all the say methods that were developed are based on some kind of heuristics. Now, first algorithm that came around in 1968 by Roth from IBM. That is called as the D algorithm, and I guess that algorithm was discussed yesterday. Then there were some shortcoming of the D algorithm, and then that D algorithm was then further. So actually, around in say early 80s or late 70s, IBM was working on memory kind of circuits, and they were using whole lot of I mean array of XOR gates, which you need to generate parity for the circuit, so that you can, so they were working on error correction codes, and there were so many I mean XOR gates in that. Problem with the XOR gate is that there is no controlling value in XOR gate. All are non-controlling value, and that makes it difficult, because if I apply 0 0 and if it fails, I have to revert every both of the input to say 1 1. So that means both in input have to change from 0 to 1, and which makes it much more difficult. Came up with another algorithm called as the say PODEM, path oriented decision making, and it says that rather than assigning value at the intermediate point, you go all the way to the primary input and assign some value, and then do the fault do the forward simulation, and check whether that satisfies your objective or not. This algorithm became almost like 100 times faster than the D algorithm. Further, the shortcoming of the PODEM were, say, in 1984 paper were say say all this so this also had a certain shortcoming about the propagation of the input, and those shortcomings were removed by Shimono and Professor Fujiwara in 1984 in their 1983 paper. And so that became the fan out oriented test, and which is called as the fan algorithm, which became almost like 100 times faster than the podem. So that means you're almost like thousand times 10,000 times faster than the D algorithm, 1,000 to 10,000 times faster than D algorithm. And this becomes more or less like a standard of almost every ATPG, say every ATPG tool that we are using today. Uh, so this fan is one of the important algorithm. Over then after that, over the time, people have developed more heuristics which can which try to find out or can capture some characteristic of the circuit and can speed it up. Socrates was one which was developed by Schulz, and then it was around 2002 2003 time period. Emil, who works now with Synopsys, uh, developed this a sequence of techniques which, if you can apply, can identify that which kind of heuristics works well for what kind of circuit, and which kind of heuristics won't work well. And now here, looking at on all those, he was able to accelerate that say uh, ATPG again by more than 10 times. So that was like that algorithm is called as Spirit. Since then, I think in 2003 4 time 2 3 time period, he works with Synopsys. Maybe one of the lead architect in that. So these are the kind of algorithms people have developed, and those are for a combinational logic. Now the question is what to do with the circuit that has these combinational logic. This is this block lambda is combinational logic, and delta is the combinational logic, because we can define all the possible inputs and can find out what is the output for those inputs. Now how to test such kind of circuits? Now, so sequential circuit has some memory element in addition to the combinational logic. There are two combinational blocks that we have, that is lambda and delta, and some memory element. Now, in combinational logic, there is no memory element, so that means here it doesn't memorize anything. Test for a fault in sequential circuit is a sequence of vectors rather than having a single vector, because the output is dependent on sequence of input, and therefore the test will also be dependent on sequence of inputs. So rather than having a one vector to detect one particular fault, you need to have a sequence of vectors to detect a fault. That makes it much more tougher exercise than the combinational logic. Keep in mind that combinational test generation itself is a uh, is a tough exercise. That's a and explore the entire possible combination. So that means if I have n number of inputs, in worst case, whether it's D algorithm, PODEM algorithm, or any other algorithm, in worst possible case, it may explore all 2 raised to the power n combinations. And if n happens to be say large, say 100, in that case, in worst case, you may need to explore all 2 raised to the power 100 combinations. And then maybe, as we discussed in very first class, the 2 raised to the power 100 combination cannot be explored even in reasonable time. It may take something like a billions of centuries. If I use one server to generate that, if I use say 1 billion server, in that case still you need a year to apply that, right? Of course we can have large number of servers, and all the big companies are using large number of servers wherein millions of processors are working together. But so that's the state we have. Luckily, things are not as bad as I am saying. Uh, as I we discussed earlier, that every fault can have multiple test vectors. So that means a fault can be tested by multiple test vectors, or one test vector can detect multiple faults. Due to this, though if the test vector exists, uh, in that case, out of multiple vectors, at least it is likely to generate one of the test vector which is capable to detect that. Say for example, for a fault, I can have 100 test vectors. Out of 100 test vectors, it is likely to say generate one of the test vector pretty fast, and that's how in practically these test ATPG tools are working reasonably fine. Though in worst case scenarios, like the way computer science people look at the complexity of the algorithm, it is NP complete, and nobody can give a guarantee that it will generate the test vector in a reasonable time. Now the question is, when there is no test vector, in that case it may keep on exploring all the possibilities, wherein this becomes difficult. So in order to deal with that, now here if I'm running my tool, and say for one test vector, if it is not able to generate the test vector for 2 days, 3 days, what to do with that? Should I continue and like wait for years to tell that here there is no test for this particular fault? So generally what do we do is we we put a limit that how many times you need to go backtrack means you have to revert your decision that you made earlier. As I said, that both line justification and fault propagation, both are the say decision making process. So then now here you have to put a limit, say that here if I'm going beyond that, it is likely that there is no test vector for that particular fault, and then I don't need to work on that. But only you can speculate that you never know that say I put a limit of 5,000. If it exceed beyond that, in that case you drop that. And now but you don't know, even in 5,000 and first attempt you may get the test vector for that. Now that particular area will become the gray area, because I don't have test vector, because I have abandoned the test generation for that particular fault. It doesn't make any difference if that particular fault is there not there in the circuit. However, if that particular fault is there in the circuit, in that case I have no way to detect that particular fault, because I don't have test vector for that. And we there So now uh, we have learned that how to generate the test for the combinational circuit. Now when I have memory in that case I have to generate a sequence of vector, and to generate the sequence of vector, then you have to initialize the circuit to the known state. If I don't initialize to the non-state, in that case I don't know, because I have no control on the say value of the memory elements. I have full control on the primary input, what I'm applying there, but what value the storage elements are holding, I don't have any control, and therefore I have to make sure that the memory element will hold some value that I want, right? So therefore, say for example, if I say that my any memory element, or all elements are resettable, in that case, in the beginning, I can I can always make that content equal to 0, right? So first I have to initialize the circuit into the non-state, and then after that we have to activate the fault. Once fault is activated, in that case you have to propagate that fault to the or fault effect to the one of the primary outputs. There can be multiple primary outputs. You have to make sure at least it has to be propagated to one of the primary outputs. So now one more step has been added before the test generation for the circuit. That means here the circuit has to be initialized to the to some known state before I write that. Now the common methods that people are the researchers have proposed and developed, and the CAD tools are offering, are based on the time frame expansion method, or based on the simulation method. Now what can happen? This is one example circuit that I am taking, is a circuit which is called as serial adder. I don't know how many of you remember what is a serial adder. Serial adder is a adder circuit that can com compute n-bit addition serially one by one. So say if I want to do the n-bit addition, in that case we can use any kind of n-bit adder. That can be ripple carry adder, that can be a carry look ahead adder, or it can be say logarithmic adder, which is like a Cogistone or Brunt-Kung or any such kind of adder. But now needs whole lot of, so if I use simple ripple carry adder, in that case I use one adder, one full adder circuit, and then replicate that n number of times, and carry generated by the left adder has to be supplied to the right adder, right? From left hand side to no, from right hand side to the left hand side, sorry, my apology. So now another way is, I in place of giving all the inputs at the same time and expecting output after a while. Now if I use the ripple carry adder, in that case the carry has to ripple all through the n say full adders. That will give me the delay proportional to the number of full adders that I have, and the number of full adders are equal to the number of bits that I have. So that means the delay is proportional to n. So I give the one input and n number of full adders I'm having, and then I'm getting output after n unit delay. A similar thing I can achieve if I can do this computation serially. So that means first I add first two elements, so least significant bits, then second least significant bits, then third least significant bits, and so on and so forth up to the last least significant bits. Now the issue here is that the carry can be generated by any addition, and then that carry has to be propagated, and therefore I have to hold the carry. If I have a mechanism to hold the carry, in that case I can do the same computation within the similar amount of time that any say combinational adder is using. So you have one storage element wherein you can take the output, and then feed back to the input, and then periodically you have to supply the input, this an and bn. and then now the carry generated from that would be supplied to the input. And now here flip flops, we are using the d type flip flops to store this value, and then those have a clock input. So that means here at the clock edge it will register the input. Whatever is available at the d, it will store, and then it will keep on providing asynchronously all the time until the clock edge arrives, and that value will remain constant. Now assume that I want to test this, and when I say so, when this, believe me, maybe you can go through this. This is a say uh, uh, one bit full adder. So that has two input an and bn, and the third input is the carry that you are getting, and then there is a output sn, and then the carry out, that carry out has to be fed back to the input. So now from the external point of view, I am providing the two inputs to this, and it is giving me the output as sn. So my controllable entities are an and bn, and observable entities is sn. Sn are always I can observe I can always provide this input as an input an and bn. But the carry out is the part of the circuit, and then I cannot observe that. So neither I can control the cn that it is feeding this to the circuit. Now, in the beginning, I don't know what value it is holding, and therefore I have to assume that it is holding value x. X can be 0 or x can be 1, right? Because we don't know. That's a gray area. And let's say that here this particular net is stuck to logic 0, and I want to develop the test for that. If it is a combinational logic, in that case perhaps you can go through the d algorithm and can generate that. Now say in using the d algorithm at the output, when what I need, this is the stuck at 0, so you have to, at the output of this fault site, it has to be generate a value d. That means my faulty value should be 0 and fault free value should be 1. So that means fault free is 1 and faulty is 0. I have to have over here. Therefore, that will set that the before this fault site, the value at fault site equal to 1. If I get value at fault site equal to 1, in that case, after this fault site, value would be 1 if there is no fault, if the value would be 0 if there is a fault. Right? So I can get the distinguishable faulty and fault free behavior. Now this is not the primary output. Primary output is Sn, and therefore I have to move this D or to the primary output, and now it has to go at the output of this particular gate. In order to move this output of the particular gate, what I need to have the non-controlling value at the another input, and that value is 1. Obviously, if I apply an and bn equal to 1, in that case this value would be 1, and therefore this d will propagate as d bar over here. I believe you have already gone through this five valued logic, wherein we have five different symbols. Those symbols are 0, 1, d bar, and x. Right? Those are the five symbols: 0, 1, d bar, and x. We have to use, so five valued algebra we have to use. Now my fault effect is over here, and I want to propagate this to the primary output. So this d bar is over here, d bar is at the input of this. Now if it is at the input of this, what will happen when I do the simulation? This value that I am getting from the flip flop is x at cn. Now this x over here will make output x over here, x over here will make output x over here, and then the output that will go to no yes, output that this value is x. The input here that I am getting as what would be the input? X and d bar is 1 0, x is x, right? The output of input would be x 0, right? So that x 0 would be x, and therefore now here when you are getting x over here, uh, this another input of this one would be x over here, and this x will give me output as x. That's the, but the output of this gate, x I am getting from here, but 1 I am getting from here. 1 is a controlling value, and therefore it will determine the output as 1. This 1 will go to this flip flop, but at the primary output I am getting value x. Therefore I cannot distinguish that what would be the value of I mean what I cannot distinguish the faulty and fault free value, because I don't know what this value would be, 0 or 1 in both of the cases. So that means this cannot be the vector for this particular circuit. Now why this is happening? This is happening because of this x that I'm assuming from the flip flop, because I have no control on the flip flop. Whenever I flip flop starts, in that case some flip flops start in state 0, some flip flop starts in state 1, and therefore I cannot say anything. That depends on how that flip flop is manufactured. And when you are manufacturing, depending on which gig say transistor has more strength, based on that it will power up in the state 0 or state 1. So I cannot say anything, and therefore now I cannot say anything about the or this value 1 1 cannot be the test vector for this. Now what to do? Now only thing is that now I got to know that this value 1 is coming out on the output of the circuit. When value 1 is coming at the CN1, that would be registered in this flip flop, and that means here it will be available in the next time frame or next cycle to the circuit. So next cycle I can ascertain that if I apply 1 1 in I mean at one time, then next cycle I know that here at least what I will have is the value of the flip flop would be 1, and I can argue something about this. So now what I can do is, if because now when circuit behaves, what happens? You apply some input, it gives you some output, and if it is sequential circuit, it memorizes the previous input, and then now you go ahead. So now I can generate a equivalent combinational circuit. So I mean equivalent combinational circuit means here I can make the multiple copies of the circuit and connect one after another one, that is equivalent to the combinational circuit. So I have one copy of the circuit. The output of that copy will go to the next copy of the circuit, and then the output of the next copy will go to the flip flop, and then this will keep on ongoing. So I can expand in 2 time, I can expand in 3 time, I can expand in 4 times, because these are the equivalent behavior of the circuit. Now the another problem start to appear, because if I make the 2 copy, in that case, in 2 copies, the the uh, the same fault will appear in both of the copies, because these are not two different circuits. For software or for the test generation purposes, we are making 2 copies in the software, whereas in hardware there is a same copy, and therefore if there is a fault in one copy, then there would be the same fault in the another copy. So earlier in combinational test generation, we were assuming that there is a single stuck at fault. Now we have to assume that there are multiple stacked faults in the circuit. You have to generate the test well within the multiple stacked fault availability. So now let's say that here I have this copy. Now within this copy, I mean this we have already discussed that I need to have D over here. So that means I'm expecting at this node output of this particular gate. Say if I say this gate Z1, gate Z2, gate Z3, gate Z4, gate Z5, gate Z6, gate Z7. So output of gate G1, I want value 1. In order to have value 1, I need to have value 1 1 at AN and BN. Now when I have this will also produce output of gate G2 as 1 as a result of having 1 1 at the input. This OR gate will produce output equal to 1. Now, when there is a fault over here, this will produce D. D means the fault-free value is 1 and faulty value is 0. Now I have to propagate this to the output. So this value has been propagated to the output, and because there is a bubble at the input, and therefore this will become D bar. Now this T bar, if I want to propagate this to the primary output, in that case, because D bar is available here and D bar is available here. Now, I mean, let's say that here I propagate through this path. If I propagate through this path, because this is closer to the output, assume that I pick this particular path. You can pick the another path as well. Now, if I pick this particular path, in that case, the D, because this is non-inverting gate, so hence D bar will propagate at the output D bar, provided that another off input of this gate will be not a non-inverting input, no, non-controlling input. So non-controlling input of an AND gate is 1. Hence, I want 1 from here and 1 from here is coming from this. So that means here I am expecting 1 from this one, which is coming from the flip-flop, right? So that means that is coming from the previous copy of the circuit, right? These inputs, so I demand 1 from this one. Now I this D bar, if this is 1, in that case this will come as D bar. If this is 1, in that case 1 is here, that means the output of this OR gate would be 1, and then this D bar can distinguish at the output that if I apply 1 1 from here, in that case my output is a distinguishable whether if circuit has fault, then it will deliver me output 0. If circuit is fault free, then output is 1. Now all these things are possible if I happen to provide value 1 over here. That is coming from the previous say copy. Now from the previous copy, in order to have this 1 over here, I have to go back. Keep in mind that this particular node has the same fault as it was earlier, so that means you're stuck at 0. Now this, you are at the output of this gate. Now this this 1 at the output you can achieve by going back and by having 1 at the one of the inputs of this OR gate. Now there are 2 inputs. Now let's say that here I will choose this one input which is coming from gate G1. If this comes from gate G1, I want 1 from here. If I want 1 from here, that means here I have to have 1 1 from AN and BN minus AN minus 1 and BN minus 1. That is the last time cycle. Now when I have 1 1 over here, in that case this will produce this fault also excites, and that excited fault will give me D bar over here. This 1 will also come from here, but then Now the from flip flop I'm getting X value here. So X and this D bar will give me X over here. This X and this D bar will give me X over here, and the so I will get this X as the output here in the previous time period, and I'm getting the distinguishable output here. So that means if I can apply a set of two vectors, first a 1 1 followed by 1 1 in that case, and ignore to watch the first time the output of the circuit, but watch only the second time the output. And if output is 1, in that case I will say it's a fault free circuit. Output is 0, in that case this is faulty circuit, right? So I need a set of two vectors. Now for set of two vectors, what I need, so I need to expand combinationally in two say circuits. So I replicate twice. Now the question is it sufficient to replicate twice all the time? And answer is no. Then how many times I should replicate this? One time, two times, 5 times, 10 times, 1,000 times? The answer is that you need to keep on expanding. So let's say that here I'm starting from this copy of the circuit that I call as time frame 0, wherein you are exciting the fault and trying to propagate to the primary output. Unfortunately, here the output can be propagated to the primary output, or may be propagated, may not be propagated to the primary output. In best case, assume that it can propagate the primary output. Then in order to propagate this to the primary output, or some output, I need some value from the storage element. Now I cannot load the value in the storage element, and therefore again I have to expand that input and try to go to a point wherein you don't expect any value from the primary input. So you may need to keep on expanding, like a time frame -1, -2, -3. You have to go to a point wherein you need only access from the storage element. That means it says that here when I power on the circuit, doesn't matter in which state it is, I will at some point in time I will put into a non-state, and after, so this is your initialization. That that step that I have told you here, this is additional step, initialization. So for initialization I need, in this case I need one time frame, but you may need to have say n number of time frame to be there. So now because there are multiple inputs. Now, in this particular case, so I need in the backward direction, that is for the line justification, that this unjustified value I have to justify through the primary input. You have to keep on expanding or making a copy of the circuit in the backward direction. And here my assumption is that in time frame 0, my fault effect can be propagated to the primary output. In this case, luckily it is propagated to the primary output, but in any general random state machine, you never know. It may not propagate at all to the primary output. It will go to the it will go to the flip flop. The output which are going to the flip flop, we call those output as pseudo primary output. These outputs we call as pseudo primary output, because they are not primary output. I cannot directly observe, but and these are the input to the combinational circuit. So output of the flip flop we call as pseudo primary input. So output may go to the pseudo primary output. If it goes to the flip flop, in that case again I cannot observe. If I cannot observe, in that case I have to keep on replicating my circuit until the point wherein my output is observable. So fault effect is observable at the primary output. So you have to for fault propagation in the forward direction, you keep on replicating the circuit, and for the line justification, you keep on replicating the circuit in the backward direction. So like here, this is the circuit. So now in the backward direction, so it if a test sequence of a single stacked fault contain n vectors, in that case you have to replicate the combinational block n times, because and now and you place a fault in each of the blocks, right? So I have replicated this n time and then place the same fault in each and every block. You generate a test for the multiple stacked faults using the combinational ATPG. I'll discuss that here. What is the 9 valued logic? Little bit. Yeah, maybe. Can I use 10 more minutes,
Yes,
or
sir,
we
please. Yes,
or
sir,
we
please.
we stop here and you can continue?
It's up to you, sir. It's up to you. No problem, sir.
Maybe 10 more minutes I can
Yes,
use them.
thank you, sir. Yes.
So far in this one problem is that we say that I have to replicate this. So and time is given, now in this test generation we use D algorithm or PODEM or FINE or any other algorithm you are using. In that case, I use the 5 valued algebra 0, 1, D, D bar, X, right? Where I mean, if one of the value, whether faulty value or fault free value is X, in that case here all we are combining in terms of in terms of X. This 0 is faulty and fault free, or both are 0. 1 is faulty and fault free, are both are 1. uh, D is fault free is 1 and faulty is 0. D bar is fault free is 0 and faulty is 1. And X is if any other value, in that case in faulty and fault free, because I need two values. So this is 5 valued logic. Now the question is, I mean, in combinational logic, it is guaranteed that if you are using the 5 valued logic, it will generate a test vector if test vector exists. That's guaranteed using the 5 valued logic. Now here, if I mean, is it still true for the sequential circuit, wherein I am converting this into equivalent combinational logic and then applying the combinational test generator? Now if I apply the combinational test generator for this, and now and use the 5 valued logic, let's take this circuit. This circuit has one AND gate and one OR gate and two flip flops, right? Very simple circuit. And let's say that there is a stuck at one fault at net A. Keep in mind that fault at the stem of the fan out, this is the stem of the fan out, is different from the faults at the branch of that fan out. So they are different, because stuck at 0 doesn't mean that it is connected to the ground. If it happens to be connected to the ground, in that case obviously that all these 3 points have to be at the same logic value. However, this is the impact of the different faults, so this may not be connected to the ground line. Now let's say that here I want to I make two time frames out of it. So one time frame, this looks like this one. Input is coming, one input is coming. Yeah, the one of the both of the input of the OR gate are coming from the flip flops, and the input of AND gate is one is coming from external input A, another is coming from flip flop one. So the one input of the AND gate is coming from flip flop A, from external input A, another is coming from flip flop 1, and then the input to this OR gate is are coming from flip flop 1 and flip flop 2. And now I replicate this and pass on the output of this AND gate to the flip flop 1, and then the output of OR gate has, I mean, gone to the primary output, right? So this is the time frame expansion. Now, in order to test this stack at 1, what I want that at the input of this fault site, I should have a opposite value to the faulty value. Faulty value is 1, so opposite value has to be 0. So I have to apply 0 over here, and then there is no problem. I can apply value 0 from this one. And when I apply 0 here, the value that I'm getting after this say faulty site would be 0 if it is fault free, and 1 if it is faulty. That is same as D bar. This is my symbol D bar. D bar comes here at the input of this AND gate. Now, one of the input that I'm getting from the flip flop would be XX. So this one input is X, input is X over here, output of this would be X, and output of this AND gate will also be X. So at the primary output, it is producing X, and at the input of the getting propagated to the primary output, nor getting propagated to the pseudo primary output. No, here it is not propagated to pseudo primary output, but this direct input is also going to this OR gate, and wherein this fault effect is propagated over here as D bar. Now it is propagated here as D bar. D bar means the fault free output is 0, faulty output is 1. Now, and keep in mind that this same fault exists in the so another input, I mean another time frame. So if same fault exists in the another time frame, means if I apply 0 here, in that case this will make us D bar. If I apply 1 over here, in that case output will remain 1 over here. What I want that this fault effect which is available here. So first thing is this fault effect I want to propagate this to the output, but this fault effect will depend on, now this is already determined, doesn't depend on the current say copy of the circuit. This output of the next time frame is also determined by the current time frame outputs, because one of the output of this AND gate is X, and this X is ORed with this D bar, and then output would be again X. So here it is not getting propagated. Now only hope is that the I excite again the fault here in this time frame or in this copy of the circuit, and can check whether I can propagate this to the primary output or at least pseudo primary output. Now in this case, if this is D, this is this X is coming, and X is going to the another input, and again I am getting this X. Now you can see that there is a periodicity. I am getting X at the flip flop 1, and X as the primary output, and this will keep on repeating. So you can, even if you do if you go infinite number of times, this will never be propagated to the primary output. Now the question is that, is it really a untestable fault? This is not untestable. Now if I look at the one time frame, I am getting D bar over here. Every time I'm getting D bar over here, but this D bar is not able to propagate to the primary output. So combinationally, I can say that this particular fault is a testable fault. It is not untestable fault. I'm saying combinationally. So, but then what went wrong? If combinationally it is testable, if the output is going to the another flip flop, and that output this fault effect remains with the flip flops. Only thing is we are not able to propagate this to the primary output. Now, so in that case, there is some shortcoming with the logic that we are using, and which is the five valued logic. In five valued logic, what we were doing, we are say adding all these say possibilities, wherein one of the whether fault free or faulty input is x, then we are clubbing all together and making a one symbol that is x. Perhaps that is one which is creating the problem. Now, in place of having the five valued, if I can use the nine valued logic, nine valued logic means I have all possibilities. Now, what those possibilities are: faulty is 0, fault free is 0, faulty is 0, fault free is 1, faulty is 0, fault free is x, faulty is 1. Sorry, the first one is fault free. That's what the convention we were using. So faulty is 0, fault free is 0, faulty is 0, fault free is 1, 0, for faulty is 1, fault free is 0, faulty is x, fault free is 1, faulty is 0, fault free is 1, faulty is also 1, fault free is 1, and are the nine possibilities. We were combining these lower four into five into one, and making the five valued logic. Now, rather than making the five valued logic, if I use all these nine values, then let's check whether we can detect this particular fault or not. And luckily we can. So therefore, the five valued logic uh, which was sufficient for test generation for combinational logic is not sufficient for the sequential logic, and we have to augment from 5 valued to 9 valued if we go for the sequential test generation. It will keep in mind that it will make the your computation more complex, because now I for every gate I have to make a table, right? And that lookup table will have 9 cross 9 say matrix, right? That will tell me that here what would be the output. It needs more storage, it needs more lookup time, and so on and so forth. Now let's say that here, is it possible? Now say if my this is the default x1, and if I want to excite, I have to have opposite value of that is 0. In that case, output, the fault free output is 0, faulty output is 1. Input here I'm using xx. So if input is xx, I can say x by x, x by x. Now, when one of the input is x by x, here output would be x by x, and x by x is we are calling as x. This I call as x. This is my 0. This is d. This is 0 by x. This is a d bar. This is 1, and 1 by x by 0, x by 1, and x, like that. These are the nine symbols that I have. So this will become x by x, and that is x. Here I have one input as x by x, another input is 0 by 1, and what output I will get? 0 by x, because this is AND gate. So 0 by x would be here, and 0 by 1 will appear over here in the second time frame. Now in second time frame, because this is the primary output. This 0 by x, it will come over here, 0 by 1 will come over here, and this is OR gate, so that means here this will give me 0 by 1, and that is valid value that I have is D, so D will propagate at the primary output. Now really I don't care anything from here. I only need to care from the first time frame value 0, second time frame can be 1, and then output I am looking at 0 by 1. So I mean, if it is 0, in that case we can say that the circuit is fault free circuit. If it is 1, in that case circuit is faulty circuit. So this will give me the faulty output. So this way, if I can augment my logic from 5 valued logic, that is 0, 1, D bar and X, to 9 valued logic, in that case I can be able to generate the test for that sequential circuit by expanding the circuit in time frame, making the combinational equivalent of that particular sequential circuit. So this will have the so I mean in when you want to develop the ATPG, in that case you have to select one of the primary output for the fault detection based on the drivability analysis. Perhaps maybe we can discuss later. Place logic value 1 by 0 or 0 by 1 depending on the fault type and the number of inversions that you have in your circuit. Then justify the output value from the primary input, like here if you are using the PODEM kind of algorithm, then you have to go all the way to the primary input, and then from that primary input you want to justify the output. So at the primary input, what you want either 0 by 0 or 1 by 1. Those are only the possibilities. So if justification is impossible, in that case select the another primary output and repeat the justification process. So this is like the iterative process we are using. Now maybe I stop over here. We will discuss in tomorrow's class that your sequential circuit can be of two type. A circuit which has cycle. Often we have circuits with the cycles, but there are circuits without cycle, so those are I mean cycle free circuits. Like for example, a circuit that you may use in say pipelining of a microprocessor. Then you have between the two stages you have some resistors, right? And in that so when you pass on some primary input, in that case after a while it will reach at the primary output, and there is no say feedback involved in that, and hence that kind of circuit is a cycle free circuit. Most of the controllers are the circuits with the cycles. So now how we need to go through this, and how many time frames I need. So in cycle free circuit, the number of times I may maximum need to unroll my circuit or make a copy of my circuit is equal to the sequential depth plus 1. Sequential depth is defined as the number of flip-flops that can occur, maximum number of flip-flops that can occur between any possible pair of input and output. That's so if it is cycle free, in that case a maximum number of flip flop that can occur between any input and output, if it is 10, in that case maximum you may need to replicate your circuit 10 11 times. However, circuit with the cycles, it is horrible. The maximum number of time that I may need to say replicate this is equal to 9 raised to the power number of flip-flops. So even if you have two flip-flops, you may need to say replicate this 9 raised to the power 2, that means here 81 times. That's that's like here almost impossible and not doable at all. So I stop over here. Maybe we'll continue in tomorrow's class. Thank you.
Thank you so much, sir. We have a question.
Ah,
One person is asking why D flip-flop is used in D flip-flop only is used in state machines. This is the question.
Maybe I defer it for tomorrow, because then see, generally maybe you may say that then why we are teaching. Generally we are not using the sequential test generators, because you can see the complexity of the sequential test generator. If I mean, if circuit is a cyclic circuit, then you may need to replicate this 9 raised to the power number of flip-flops, and with the even with the 2 flip-flops I may need to replicate this 81 times.
Thank you, sir. Any other question from the audience? Please feel free to type in the chat box, or you can raise your hand. We can unmute you.
It's so because of that, and some more issues I will discuss tomorrow. Because of that, in general we are not using sequential ATPG. Therefore we want to use the combinational ATPG, and for combinational ATPG we have to augment the circuit. That is called as design for test. Now when I augment the circuit, that augmentation put this requirement that any storage element that I have should be directly readable and directly writable. Therefore, it should have one input and one output.
Thank you so much, sir.
And because of that, it is only D and D master slave D flip flop which is being used in the in practice.
Okay, sir. Thank you so much, sir. It was a nice talk. First, you have discussed the remaining part of the memory testing, where various March tests and how those tests are going to cover maybe the address decoder, or maybe the transition faults, or maybe some other faults. It is going to sticket faults. It is going to cover those you have discussed. After that, sequential testing you have covered the 9-value algorithm, how it is important in the sequential testing instead of like 5-value algorithm. That is for sure is going to give us the test vector if possible there in the combinational circuit, but that is not applicable always in the sequential circuit. So the 9-value algorithm is actually the one which is going to give us the solution. And you have also discussed the time frame expansion algorithm also for the sequential circuits. So with this, we are having our first session over. Thank you so much, sir, for your talk. And we will be waiting for your next discussion tomorrow, sir. Thank you, sir.
Thank you. Thank you.
So, dear participants, we will be connecting back in 5 minutes. Please let us to switch the session so that we can switch the session and then we can reconnect. Thank you so much. Gaurav and Satveer, may I request you to switch the session, please?
Okay, ma'am. Okay, we will do that.
So we will be back at 11:35. Thank you, sir.